Okay, magandang umaga ulit. We are now in the second part of our lecture about more on triple integrals in rectangular coordinates. And now we start with slide number 7, where we tackle one concrete example of a triple integral over a solid that is of type xz. Okay, so we are given with this problem. Let's evaluate the triple integral of, so if there's no integrand here, as what we have been accustomed to, this would be 1, no? So the triple integral of 1 dv over g, where g is bounded by the planes x equals 0, so x equals 0 is nothing but the yz plane, y equals 0 would be the xz plane, z equals 0 is the xy plane. So all the coordinate planes are here. Then 2x plus z equals 2. So again, when you see something that has a missing variable, you can treat this always as a cylinder. That means that how do you draw this? You look at the xz plane, this is the xz plane, and then you draw this line, no, 2x plus z equals 2, and that's easy because you can just look at the intercepts. So the x-intercept is equal to 1, the z-intercept is equal to 2, this line. And then what you do to generate the whole cylinder is to propagate it along the axis of the missing variable, which is y. Okay, so this is your plane 2x plus z equals 2, right? And then, aside from that, there's another boundary, which is again a cylinder, which is a plane also. Y plus 2z equals 4. So this is a plane whose generator is on the yz plane. So the y-intercept would be 4. The z-intercept would be 2. And then you draw this line on the yz plane and propagate it along the axis of the missing variable, which is x. Okay, so after doing that, you discover that there's a line of intersection here, uh, and this is the solid. So I hope you can draw that by yourself. Now, what is the problem of this solid? Why can't we treat this as a solid of type xy? So I told you before that it's very natural to treat solids as a solid of type xy because projections, diba? When we think of projection, you always project to the ground, and the ground is the xy plane. But what is the problem here if you project it on the ground? So sure thing, the projection is nothing but this rectangle, but that's not the only condition for a solid to be of type xy. It must be that at any point xy on the region, there must be a single ceiling and a single floor. So the floor is not difficult because the floor is simply the same region as the projection, but the ceiling is different because, right, points that are to this direction, the ceiling is the blue surface, which is this surface. But if you look at this point, the ceiling is the pink surface. So there is not one ceiling function for this solid. That's why if you force this solid to be of type xy, then you have to subdivide the solid into two. So and then use the additivity property of triple integrals, that the triple integral over this solid can be written as a sum of triple integrals over the two solids that have been divided, that you have after division. So to make things simpler, we view this in another way. So if this is not a simple solid of type xy, then is it a simple solid of type xz? So let's look at this again. Is there a projection onto the xz plane? So yes, there is a projection onto the xz plane, and it's nothing but this triangle over here. And then again, the next question is that for all xz on that projection, can you well define, now can you define clearly the ceiling and and the floor functions of the solid, and the answer is yes. So the floor function will be the same projection region, and the ceiling would be this, the pink surface. So at any point xz, it is always the case that the lower limit will be from this surface and the upper limit will be from this surface. So this is a simple solid of type xz, and we can solve the triple integral using just one evaluation, right? So always, and I think I have not emphasized this before, when we try to evaluate triple integrals, there are two things that we need to draw so that the limits of integration would be clear to us, and that is the three-dimensional object and as well as the projection. You have to draw it in a separate Cartesian plane. So here I just redraw this triangle into this. So this is again the z-axis and this is the x-axis. So you see that 2x plus z equals 2. It is the same equation as this one because, well, this line is the intersection of this plane and y equals 0 and y is absent from this equation. So it's still the same equation. Okay? So how do you evaluate this again? So let's go to the next slide. So, ginawa na niya agad itong triple integral. But let's do first the intermediate step. So, you have double integral over r, and this is r dA, right? So, the innermost integral will be an integral with respect to dy, because r is a region in the xz plane. So the innermost integral would be an integral with respect to y. And how do you get, okay, so this is still, the limit of the integral is still 1. Okay, it doesn't change. So what you need to find out now, what we need to find out now are the limits of integration of the innermost integral. So again, we look at a particular point on the xz plane and then try to find the surfaces that define the floor and the ceiling of the solid. So again, the floor is this, right? And the ceiling is this. Okay. So what is the equation of this surface? So the equation of this surface is, it is the surface of the xz plane, which is y equals 0. So that means that the floor function is 0, y equals 0, and that's the xz plane, right? And what about this one? What is the equation of this triangle? So the equation of the triangle is this, y plus 2z equals 4, and you want to write that in terms of y, so y would be equal to 4 minus 2z. So maybe I'll write here y equals 4 minus 2z, which is just a restatement of that equation. So now we have this intermediate step. This will now be the definition, no, of this triple integral as so it's not yet an iterated triple integral because you still have this double integral to deal with, but you have this you have this drawing of the region, and you can clearly well, this is either a type 1 or a type 2 region, and if you did well on double integrals, you can easily supply the limits of integration for this double integral. Okay, so so you see here that we get the same innermost integral, right? And what about this one? So maybe you try, how is it treated? We treat this as a type 1 region. So type 1 region means that you look at the vertical strip and, okay, and look at the top and the bottom functions. So remember that this is the x-axis and this is the z-axis. So therefore, this is the line z equals 0, and this is the line z equals 2 minus 2x. And therefore, the limits of integration for the second innermost uh, the second innermost integral will be 0 and 2 minus 2x, and then z here, and then x here will range from 0 to 1. So you see 0 to 1, 0 to 2 minus 2x, right? Oh, no, no, why is it 4 minus 2z here? So, sorry, it should, yeah, yeah. So, no, no, this is 2 minus 2x here, but it's still r. No, what am I doing? Okay, okay. Um, so here you have 0 to 2 minus 2x, reflecting this bottom and top functions, and then 0 to 1 reflecting the range of x. Okay, 0 to 1. So this again, I told you before that in evaluating double or triple integrals, the setting up of the integral into this iterated form is the most important, and it will give you the most number of points in this solution. So for instance, if this is 4 points, then arriving at this will give you at least 2.5 points, and the others will, or 3 points maybe, and the others will just be checking whether you were careful in integrating. So for instance, what is the integral of 1 dy? It will be y, and then you evaluate from 0 to 4 minus 2z. So I'm not gonna bore you with these details because you've done that in Math 21 and Math 22 as well. So this is equal to that one, which gives us the final answer of 8/3. Okay. So the next part will be another solution of this one if we force ourselves to treat this as a solid of type xy. And let's have another example afterwards.